Okay, good afternoon, good evening. My name is Duncan Jones, and I'm the head of cybersecurity at Quantinuum. And I'm joined today by my colleague Jefferson, who's one of our lead scientists, and also by Naniwada-san from our partner Mitsui in Japan. So yeah, we thought three speakers might be better than one, just to keep you guys awake for the last few minutes before happy hour. Actually, earlier this afternoon, I was using ChatGPT, and I was trying to get it to help me with a quantum joke about three people, and I was thinking about GHZ states, and maybe there's something there. And if you go look at ChatGPT now, it's broken. So, read into that what you will. Anyway, so getting to the topic. So today we're going to be talking about something interesting we've been working on over the last year or so, which is a concept called quantum tokens. So it's a new concept that we think will have some revolutionary impacts for financial services. So structure of the talk, I'm going to give a bit of a background as to why we're looking at this and why we think it's interesting. I'm going to pass to Jefferson, who will talk about how this actually works. And then we'll pass to Koji, who will then talk a little bit about use cases and where we see the applications for this. So I'm going to start by going back in time about 40 years or so. So back in the 80s, some really seminal papers were released that led to the field of quantum key distribution as we know it today. So in particular, there was this one paper published back in 1983 by Wiesner called conjugate coding. And that sort of, I think, laid the groundwork for how we might use quantum states to do interesting things in cryptography. But if you have a look at that paper, and I do encourage you to have a look at it if you've not seen it before, the second use case that's described is actually nothing to do with cryptography. It's all to do with finances. And it's recognizing this idea that quantum information actually could be a really natural method for representing money. Now, if you think about the benefit we get from QKD is that, let's say I'm sharing a key with Jefferson using QKD. I know through the laws of physics that only one key is going to arrive, and I can double check that it arrived to Jefferson. So if you think about that from a monetary perspective, if you want to send money to somebody and you want to have absolutely a guarantee that no duplicate spending is possible, or that I send Jefferson one piece of money, he can't somehow turn it into two pieces of money and spend it in two different ways, you can see how quantum can potentially provide some advantages here. Now, there is a problem, though. The reason why we don't have quantum money today is because we don't have quantum wallets, right? So quantum information is extremely fragile, and a lot of people, including some folks I know in the exhibition hall, are working very hard to figure out how do we actually store this stuff for any length of time. But right now, the state of the art is seconds, minutes. It's short. It's nothing like the hours, days, or years that we would need in order for us to send money and forget about it and get it back 6 months later. So this is what has motivated our exploration of this new technology called quantum tokens, because it blends together the quantum world and the classical world, and it allows us to realize a lot of the benefits of quantum money, but without the need for the quantum memories that we don't have. So the benefits that I'm talking about, there are three that we think are interesting and that we can deliver today using quantum tokens. So the first is this unconditional unforgeability that I was talking about earlier. So in the same way that QKD guarantees this one key, we can guarantee one token arrives. So that's very interesting. And this all just comes down to the no cloning theorem. The second thing, which is more of a property of how this particular protocol works, is that we can actually speed up transactions as well. So when Jefferson, and sorry for picking on you, Jefferson, but when Jefferson turns up to a shop or wherever to spend his quantum token, there's no need for that shop to verify with a central authority or do any kind of cross-checking to ensure that there hasn't been double spending here. And then the third property is more of a hygiene factor, but privacy is important. And we want to make sure that before Jefferson spends his quantum token on something, that nobody has an idea of what he's going to spend it on. That should be private. His intentions should be private to him. And so any system, any financial system usually wants to try and adhere to that principle. Okay, so I'm pausing for a second because I can see that our last changes to the slides haven't gone through. So I'm going to skip over a slide. Don't look. close your eyes, close your eyes. And I'm going to go to this slide, and then we'll come back to that. So I just want to compare and contrast these three properties versus things that we know today. So if we think about banknotes, so banknotes can deliver two of these three properties. So banknotes are definitely not unforgeable. You know, they try very hard to make them difficult to forge, but it's not anywhere close to unconditionally forgeable. You could definitely get away with spending dodgy dollars somewhere if somebody's not paying attention. But there is local validation. So by that, I mean, if you take your dollar note and you give it to, you know, a cafe, they don't call up anybody. They don't check if you've got money in your bank account. They just take your dollars and they give you your coffee, right? And then user privacy is also there. So nobody knows what you're going to do with that dollar bill before you spend it. Classically, so looking at classical cryptography, we can achieve any two of these three properties, but never all three at once. So there's different solutions that trade off different things, but somewhere along the line, you have to give up on one of these things. And with quantum tokens, we're able to achieve all these three things simultaneously. And that we're not aware of any classical solution that can do that. So I'm going to pass over to Jefferson here, and hopefully we can navigate backwards so that you can cover from here. Thank you, Jefferson.
Thank you. Let's see if we can. Yes, OK. So let me start by introducing the characters in our protocol. In quantum cryptography, we usually talk about Alice and Bob. In this case, we're going to talk about the bank, which is the authority that issues the token. And we will have an user. This is the person or company or an entity that is willing to use the token to redeem it for goods or values later in a branch. So we have the bank that sends the token to the user. And here it's important to say that we are sending this information using QKD hardware. So this means that the bank is using the same idea back from the 80s from Wisner, where the information is encoded in conjugate bases. And this uses, for example, photons or laser pulses that encodes this type of information. And then on the other side, what the user does is to measure these quantum states in the encoding bases. And the key part here is that the user stores this information as classical information. So when the user measures these quantum states coming from the bank, then there is no need for a quantum memory anymore. So the user measures the quantum states, stores them as classical information in a usual memory, classical memory, for later redemption. But then somehow we need to compensate for the fact that we're not using quantum memories here anymore. And we compensate that by using an intermediate step between having the token and redemption later by the user. And that part is called commitment. So in this stage, the user commits to a specific branch from the bank where he will redeem the token later. But more importantly, this commitment part is in such a way that the information, the commitment information is sent to the bank, but there is no way the bank knows in advance where the user will redeem the token. And this is what we meant by user privacy. The bank or the branches or the stores don't know where the token will be redeemed. So here we have the third character of this full picture, which is the branch. We can have two or more branches. Here we have pictured only one, but this is the place where the user will redeem the token later. Let's assume we have two. In the next slide, I will explain more how the protocol works step by step. But let me emphasize here another important property of quantum tokens, and it is the fact that when the user comes to the branch doesn't need to call to the bank to authenticate the token. The branch is not calling the bank asking, is this token valid or not? There is no cross-checking here. The branch is able to authenticate the token without that cross-checking. And this is an essential part of the protocol to guarantee the speed up and the fact that the protocol is fast enough. And this is what we call local validation. There is no need for the branch calling the bank and validating the token after. So now let me skip this slide. And let me describe how the protocol works from a bigger perspective. So we have here again our 3 characters. The first, the bank. Then we have 2 branches that we labeled 0 and 1. And then we have a user for the token. We can have more branches if needed and if we want. But so far, just to keep things simple, we will have 2. So the user decides to use quantum tokens because of all the advantages and the lack of quantum memories. So he decides to start a quantum token session with the preferred bank. And then the user requests a token from the bank. The bank gets this token request and sends the token to the user using QKD hardware. After the user gets the token from the bank, what he does is to storage the information, as I said, classically, measure the quantum states and store them, that information in a classical memory. And then also, it's important that the branches receive the information about the token. So let me make a comment, an important comment here. Here we have 2 roles. This is the bank and the user that don't trust each other. This is in contrast to QKD, for example, where we have the Alice and Bob that trust each other, and then there is a third party that is trying to intercept the communication between Alice and Bob. Here it's different in the sense that the bank doesn't trust the user because the user can double spend the token, for example. And this is really bad for financial transactions or commodity-based tokens. So here, the bank and the branches are trusted entities, but the bank and the branches don't trust the user. So here the branches get the data, classical information about the token preparation that the bank sent to the user. Now, in the third step of this protocol, the user commits to a specific branch. And the way in which the user commits to, let's say, branch number 1 is by encoding the branch information somehow. It's basically generating a random bit and performing an exclusive OR operation. Then the branches receive this commitment information. And finally, later on, when the user is ready to redeem the token, then the user sends this information, the redemption request, to either branch 1 or branch 0, or both at the same time. But since the branches don't need to call the bank to authenticate the token, then they can either validate or reject the token redemption. And this is exactly what we are showing here in the last step, where let's say the user committed to branch number 1. So the branch number 1 can successfully redeem the token. But even if the user submits the token at the same time at branch 0, the branch is the branch 0, that branch will reject the token because that wasn't the one the user committed to in the first place. With that, I will like to pass the remote control to our partner, Naniwada-san, who will explain what we did in real life.
Thank you, Jefferson. So this slide shows the overview of demonstration system in Tokyo. On the left side, we can see QKD, commercial level QKD transmitter, which is provided by NEC, and which is corresponding to the bank, which Jefferson explained. And on the right side, we can see QKD receiver, which corresponding to the user. And also we use 10 kilometer optical fiber in this demonstration. This picture shows a scene of final demonstration in Tokyo, last October. And we can see demonstration system in the center, and also many key persons attending to this demonstration, both Quantinuum and Mitsui side. And let me explain who is Mitsui and what we are expecting to this quantum token. Mitsui's origin is a trading company established almost 80 years ago. And now we have a variety of business, including oil and gas trading and transportation, and also asset trading. And now we are trying to develop digital trading business by utilizing AI, blockchain, and quantum. For example, we are providing security token solution for real estate asset. And the security level and immediacy of quantum token are very attractive for our business, since these characteristics is very important for digital trading businesses. So we think these three use cases is promising for quantum tokens. First one is a high-speed financial transaction, with, including HFT type of transaction. And near instant validation give us competitiveness in this region. And second one is commodity-backed token. If we think a huge variation in this region, high-level security is very important for commodity-backed tokens. And also, we can use quantum token as a kind of authentication method. So in that case, very high security and instant access to database is another promising use cases.
Okay, thank you. I think they might have muted me now because of all the coughing. Sorry about that. So just to wrap up here then, so we've walked through what our recent experimental work has been all about. And so we're now at this stage of moving towards developing our first commercial products based around this technology. A big part of that is to grow our industry partners and technology partners. So I guess the call to action from this presentation is that if you're intrigued by this, either as an organization that can see use cases for these sorts of high-speed transactions, or if you do cool quantum stuff and you just want to get involved, then please do let us know. And we'll be working with those partners and looking to expand some of these use cases, potentially also involving some adaptation of the hardware as we narrow in on specific use cases. So that brings us to the end. We do have a booth, and we are, I think, jointly sponsoring some drinks that are appearing in about 10 minutes in the exhibition hall. So do stay for the next talk, but then go straight from there, grab a beer, and come speak to us about quantum tokens, please. Thank you very much.